Hello all. Today we are going to discuss about JPEG. JPEG stands for Joint Photographic Expert Group. JPEG is one of the most popular and comprehensive continuous tone steel frame compression standard is a JPEG standard. JPEG is the loosey image compression method. JPEG compression uses the DCT, that is discrete cosine transform method, for coding transformation. It allows a trade-off between storage size and the degree of compression can be adjusted. It defines three different coding systems. First one, a loosey baseline coding system, which is based on the DCT and is adequate for most compression applications. Second one, an extended coding system for the greater compressions, higher precision or progressive application. And third one is a lossless independent coding system for reversible compression. To be JPEG compatible, a product order system must include support for the baseline system. No particular file format, spatial resolution, or the color spatial model is specified. The figure shows from A through F shows 6 threshold coded approximation of the monochrome image. In figure A, all images were generated using 8x8 DCT and normalization array. The first result, which provided a compression ratio of about 12:1, was obtained by directly application of that normalization array. The remaining result, which compressed the original image by 19, 30, 49, 85 and 182 to 1, were generated after multiplying the normalization array by 2, 4, 8, 16 and 32 respectively. The corresponding RMS error are 3.83, 4.933, 6.62, 9.35, 13.94 and 22.46 intensity level. In the baseline system, often called the sequential baseline system, the input and the output data precision is limited to 8 bits, whereas the quantized DCT values are restricted to 11 bits. The compression itself is performed in 3 sequential steps, that is DCT computation, quantization and variable length code assignment. The image is first subdivided into the pixel blocks of size 8x8, which are processed left to right, top to bottom. As each 8x8 block or sub-image is encountered, its 64 pixels are level shifted by subtracting the quantity 2 raised to k by 1, k minus 1 transform of the block is then computed, quantized in accordance with and reordered using the zigzag pattern to form a 1D sequence quantized coefficient. Let us consider the example, that is JPEG baseline coding and decoding. Consider the compression and reconstruction of the 8x8 sum image with the JPEG baseline standard. First, the original image consists of 256 or 2 raised to 8 possible intensity, so the coding process begins by level shifting the pixels of the original SIP image by minus 2 raised to 7 or minus 128 intensity level. The resulting shifting array is in this way. Then, which when transformed in accordance with the forward DCT of for n is equal to 8 becomes in this way. If JPEG recommended normalization of an array is used to quantize the transform array, the scale and the truncated, that is normalized in accordance with the coefficients, are then in this way. Then, where for the instant the DC coefficient is computed as T cap 00 is equal to round T00 by Z00, that is round minus 415 divided by 16 is nothing but minus 26. In this way we are finding all the values, minus 26, minus 1, minus 3, minus 6. Note that the transformation and the normalization process produces a large number of zero value coefficients when the coefficients are reordered in accordance with the zigzag ordering pattern. The resulting 1D coefficient sequence is minus 26, minus 31, minus 3, minus 2, minus 62, minus 41, minus 41150200, minus 120000, minus 1, minus 1 EOB, where EOB symbol denotes the end of block condition. A special EOB Huffman code word is provided to indicate that the remainder of the coefficient in a reorder sequence are 0. Then we are discuss about predictive coding. Predictive coding states that the brain continually generates the model of the word based on context and information from the memory to predict sensory input. In terms of brain processing, a predictive model is created in a higher cortical areas and communicated through feedback connections to lower the sensory areas. Predictive coding is based on eliminating the redundancies of closely spaced pixels in space and or time by extracting and coding only the new information in each pixel. The new information of the pixel is defined as the difference between the actual and the predicted value of pixel. Then there are two types of predictive coding, that is lossless predictive coding and lossy predictive coding. We have discussed one by one. First one is lossless predictive coding. The system consists of an encoder and a decoder, each containing an identical predictor. As successive example of discrete time input signal, that is f of n, are introduced to the encoder, the predictor generates the anticipated value of each sample based on the specified number of past samples. The output of the predictor is then rounded to the nearest integer, denoted f by n, and used to form the difference or prediction error, that is E of n is equal to f of n minus f cap by n. F of n is equal to E of n plus f by n, which is encoded using a variable length code to generate the next element of the compressed data stream. The decoder reconstructs E of n from the received variable length code word and perform the inverse operation, that is f of n is equal to E of n plus f bar n, to decompress or recreate the original input signal. This figure represents lossless predictive coding model, encoder and decoder. Various local, global and adaptive methods can be used to generate f cap n. In many cases, the prediction is formed as a linear combination of m previous samples. That is, it can be written as f bar n is equal to round of summation of I is equal to 1 to m alpha j f of n minus I, where m is the order of the linear predictor, round is a function used to denote the rounding or nearest integer operation, and the alpha I for I is equal to 1 to up to n are prediction coefficient. If the input sequence is considered to sample of the image, the f of n and the m samples are used to predict the value of each pixel come from the scan line from the current and the previous scan line, or from the current image or the previous image in a sequence of an image. Thus, for a 1D linear predictive image coding can be written as f cap x of y round summation of I is equal to 1 to m alpha I f of x comma y minus I, where each sample is now expressed explicitly as a function of the input image's spatial coordinate x and y. Figure represent lossless predictive coding. Figure B and D shows the intensity histogram of the image A and the histogram of the prediction error E of x comma y respectively. Note that the standard deviation of the prediction error in a figure D is much smaller than the standard deviation of the intensities in the original image. Moreover, the entropy of the prediction error is significantly less than the estimated entropy of the original image. This decrease in entropy reflects the removal of the great deals of the spatial redundancy, despite in fact that of k-bit images. k plus 1 bit numbers are needed to represent the accurately prediction error sequence E of x comma y. In general, the maximum compression of the predictive coding approach can be estimated by dividing the average number of bits used to represent each pixel in the original image by an estimate of the entropy of the prediction error. In this example, any variable length coding procedures can be used to code E of x comma y, but the resulting compression will be limited to about 8 or 3.99 or 2:1. The next type of predictive coding is lossy predictive coding. In this type of coding, we add a quantizer to the lossless predictive coding model and examine the resulting trade-off between reconstruction accuracy and compression performance. As a figure shows the quantizer which replaces the nearest integer function of the error-free encoder is inserted between the symbol encoder and the point at which the prediction error is found. It maps the prediction error into a limit range of the output denote E.n, which establishes the amount of compression and distortion that occur. In order to accommodate the insertion of the quantization step, the error-free encoder must be altered so that the prediction generated by the encoder and the decoder are equivalent. As shown in figure A, this is accomplished by replacing the lossy encoder predictor within a feedback loop where its input denoted f.n is generated as a function of the past predictions and the corresponding quantized error, that is f.n is equal to E.n plus f cap n, where f cap n is as defined earlier. This closed loop configuration prevents the error build-up at the decoder's output. This is all about the lossy predictive coding model, that is encoder and decoder. This is all about the encoder and decoder. The quantized error is given by the formula for a lossy predictive coding is f.n is equal to E.n plus f cap of n. Then next type of coding is wavelet coding. The wavelet coding is based on the idea that a coefficient of the transform that decoded relates the pixel of an image can be coded more effectively than the original pixel themselves. The wavelet transform can be used to analyze the signal in time frequency space and reduce noise, while retaining the important components in the original signals. In the past 20 years, WT has become a very effective tool in a signal processing. If the basic functions of the transform, in this case the wavelet, pack most of the important visible information into a small number of coefficients, the remaining coefficients can be quantized coarsely or truncated to zero with a little image distortion. This figure represents the wavelet coding model, that is encoder and decoder. To encode a 2⁻ by 2⁻ image and analyzing wavelet phi and minimum decomposition level G, J minus P are selected and used to compute the discrete wavelet transform of the image. If the wavelet has a complex and complementary scaling function phi, the fast wavelet transform can be used. In either case, the computed transform converts a large portion of the original image to horizontal, vertical, and diagonal decomposition coefficient with a zero mean and the Laplacian-like probabilities. Because many of the computed coefficients carry little visible information, they can be quantized and coded to minimize intercoefficient and coding redundancy. Moreover, the quantization can be adapted to exploit any positional correlation across the P decomposition level. One or more lossless coding method like run length, Huffman, arithmetic, and bit plane coding can be incorporated into the final symbol coding step. Decoding is accomplished by inverting the encoding operation with the exception of quantization, which cannot be reversed exactly. The wavelet chosen as the basic of the forward and inverse transform affect all the aspects of wavelet coding system design and the performance. They impact directly the computational complexity of the transforms and lays directly the system's ability to compress and reconstruct images of acceptable error. When the transforming wavelet has a spanning scaling function, the transformation can be implemented as a sequence of digital filtering operations with the number of filter tabs equal to the number of non-zero wavelet and scaling vector coefficients. The ability of the wavelet to pack the information into a small number of transform coefficients determine its compression and reconstruction performance. The most widely used expansion function for wavelet-based compression are Dosy wavelets and biorthogonal wavelets. This figure contains 4 discrete wavelet transforms. Higher wavelets, the simplest and the only discontinuous wavelet considered in this example, were used as the expansion or the basic function. Dosy wavelet, among the most popular imaging wavelets, were used in figure B. Simulates, which are an extension of the Dosy wavelet, will increase the symmetry, were used in a figure C. The Cohen Dosy Fourier wavelets that were employed in figure D are included to illustrate the capability of biorthogonal wavelets. As in the previous results of this type, all the details coefficients were scaled to make the underlying structure more visible with the intensity 128 corresponding to the coefficient value 0. This is all about the wavelet coding. Thank you.